Let's look at another quantity then, which is a radiation pressure. Radiation also carries momentum, so it exerts pressure over a surface. To know this pressure, we need to look at the momentum that a radiation beam is carrying. Now, to get the momentum flux, we have to recall that the momentum of a photon is the energy over c. You recall that energy is equal to Pc. P is the momentum and c is the speed of light. So the momentum is E over c. Now, the momentum is a vector, just flowing then in the direction of the beam, which is this direction here. So we can write that a single radiation beam carries an infinitesimal amount dp, and this infinitesimal amount of momentum is equivalent to the infinitesimal amount of energy that it carries. Now, because we defined this energy also per frequency, this is the momentum carried in a frequency range. So let's give subscripts nu to this. And now we can define this in terms of intensity. Write dA d omega in terms of the angle between them. The pressure is found by finding the normal of this momentum to the area element. Now, the area element is normal to the perpendicular to the surface, and call this n hat. So the pressure has a parallel component to the surface, which would be this one, and it has a perpendicular component to the surface, which is this one. And of course, it is only the perpendicular component that exerts pressure. So what you are interested in is this perpendicular component. Substituting the expression for the differential of the pressure, and the angle between them is the same angle as the angle between the radiation beam and the normal to the area, which is the same angle theta between the area differential and the solid angle differential. So we ended up with the square of the cosine. Now, the pressure is the force over the area. So we can write the differential d capital P, the differential pressure, is the force, which is the momentum over time, over the area. And substituting the expression for the differential of the perpendicular momentum, that becomes, now if you divide them by the bandwidth, the frequency bandwidth, you have the specific pressure. And if you finally integrate over all directions, you have the total pressure. So based on the pressure, we can construct a pressure equation for the star. Let's first get to the equation of radiative transfer and multiply it by cosine theta. So we have cosine squared theta di d tau is equal to I cosine theta minus the source function times cosine theta. Now integrated is an angle. So you have the integral in the left-hand side is the pressure. The first integral on the right-hand side is the flux. And the last integral integrates to 0. So what you have in the end is a relationship between the pressure and the flux, reinstating the frequencies. Again, this is an interesting result. The left-hand side is a pressure gradient. That is, it is a force. So this equation states that this force arises directly from the radiation pressure. So we have then this set of equations for the atmosphere. The divergence of the flux is 0. Bolometric absorption is equal to bolometric emission. And the pressure gradient is the flux. So these are the three equations for an atmosphere in radiative equilibrium.